Okay, what is up? It's your boy the Knologist. We're going to be doing another Leetcode today, and it's called the power of 2. Now, for the people asking why not do the power of 3, I don't know, bro. I can't tell you. I couldn't tell you. So given an integer n, return true if it is a power of 2. Otherwise, return false. An integer is a power of 2. There exists an integer such that n equals 2 to the power of x. Okay. So n equals 2 to the power of x. Okay. So if n equals 1, 2 to the power of thing. If n equals 2, 2 to the power of whatever. N equals 3. So n equals 4. So n equals 16, 2 to the power of 4. N equals 1, 2 to the power of 0. N equals 3 false. Okay, cool. I think you have to do the opposite of exponent. I think it's like logarithm, log base 2. How to get the base of a number using log, rewriting the log into exponential form, how to find the base of a logarithm. Okay. So for example, log b 27 equals 3. Find the base of the log. Find the base of log 27. So log in Python, math.log, x base. Okay, cool. Does it show us how to use it? So math log 2. Okay, so let's try it yourself. Math log 2. Okay, so math log 2, math log 1 equals 0. Okay. Log 1 base. Let's try base 2. Let's just see. I just want to see what it's going to do. 0. Okay. Math log base 2. Base value. Okay, I know the base is 2. So for example, it would technically be log in Python. Log in Python math.log method math.log log x base, which is natural logarithm, or the logarithm of number to base. Okay, let's go back here. N equals 1. N equals 16. (16) to base 2 equals 4. 3. All you have to do, if it's a power 2, is figure out figure out the base using the power. So if I go math, do you have to import math? Yeah, you have to import the math library. So for example, if I do this, import math, then I go to base math dot log, and this is the base, right? So if I know it's base 2, n is a value, an integer. Oh, I could just check if it's a whole number. So if math.log base 2, it should give me an exponent. If it's not, then it's thing. So if math n base 2, I should get the exponent. So 16 base 2, I should get 4 as my exponent. That's the log. That's the exponent I'm trying to get. Because 2 to the power 4 is 16. So if I do log base 2 of 16, I should get 4, right? So that's the opposite. If math.log is not a whole number, it's not an exponent. So therefore, it's not a power of 2, right? So let's put check if a number is whole in Python. Maybe I'm doing this wrong, right? It's been a while since I've done all this shit. Check if a number is whole. Check if a number is decimal. So is instance, or check if float is an integer, Is instance I int? If that's the case, I could just return is instance math.log int. What? Why doesn't that work? So for example, 1 base 2 power 0. Oh, does 0 count as an int? I'm just curious. Let's go to Python Playground. I just want to check if 0 counts as an int. So we go Python Playground. I go. True. Okay. I'm just curious now as well. Let's take it a step further. Let's import math. Ah, 0.0. This is a fucking float. That's why. That's why. It's not going to return int. It's going to return float. I need to return int. Math.log int. It returns a float. Oh, I could just go is integer. Okay, okay, if that's the case. Is integer. Return true if the instance is thing, otherwise false. Okay, cool. 1.5 dot is integer. Is integer. Okay, so this will return 0.0. Let's say if I put 1. So then if I go math.log is integer, that should give me 0. Why? Is integer. Is integer. Does that not work? Is integer. PHP. Does that? It doesn't exist. Okay, what the fuck? Where the fuck do I go? Okay. I'm just curious. I'm just curious to see if it'll work. Yeah, it does. Is integer fucking works. Okay, I don't know what the fuck is going on, but it works. So basically what I'm doing is if math.log 2 to the power, so exponents and logs are inversely proportional. So log of 4 is going to be base 2. Yeah, log base 2 of 4 is going to be 2. 2 to the power of 2 equals 4. So whatever the exponent is, it's gonna be the opposite. You switch them for the fucking logarithm, right? So if I go math log n2, right? I'm going base 2. If I take 1 base 2, it would be log of 1 base 2 is 0, right? And then 2 to the power of 0, so that base 2 to the power of 0, whatever that is that I just logged, should be 1, right? So I'm doing this here. The only thing is with this logarithm function is that it returns a float. So if it returns a float, I want to know if that float number is equivalent to a whole number integer. So what I do is then I take isInteger, this function, and then I attach it to the end of this log. So let's say I get 16, right? So log of 16 base 2 should be 4, because 2 to the power of 4 is 16. So if I get 4.0 for my math log of 16 base 2, right, my isInteger function should then check, okay, is 4.0 equal to 4 the integer? Yes, then true. Submit. What? What the fuck? It literally works on all of these. Why? Why? Expected true output false. Expected true output false. Why? Why is this not working? Log of this base 2 is integer. It should work. What? It pretty much works for 1,086 test cases out of 1,110 test cases. Why? Why the fuck does this not work? Okay. Okay. Description. Let's just put it on ChatGPT. I want to find out why. Can you solve it with loops, without loops / recursion? Yes. I just use logarithms. But I want to know why these guys aren't. So int. Like why? Why? I would say my solution is far more than adequate. This is my code. And I had a one-liner too. I want it to be like intellectual and shit. Be like, yo, check out my fucking one-liner. Right? Let's see. I want to see why my one-liner didn't work. Your current approach is power 2 is generally correct, but there are some considerations and improvements we can make. Okay. You should handle a case where n is less than or equal to 0 separately. Okay, wait, what's the conditions for this? What's the conditions for this? It could be negative. Okay. But still. It should still hold true. Okay, you should is less than or equal to 0 separately, because according to the problem statement, negative numbers and 0 are not considered powers of 2. Using floating point math, because there's just precision issues with very large or small integers due to floating point arithmetic. Okay. What? Negative 0 check. Okay. Okay. It's still kind of a one-liner, because you're basically saying if it's less than 0, it's not a power of 2 anymore. Because powers of 2 can only be positive. Okay, so that does make sense. So I put if n is less than or equal to 0, because you can only have power 2 to the power 0 is 1. Return false. I'm just curious to see if this works, right? Because generally this would work. I just want to see. Okay, 1,109 out of 1,110 test cases pass. You gotta be kidding me. They did this intentionally for me not to use math.log. So then, okay, if I do this, then I go return. And then use AND gate with n minus 1. Let's see what they did here. Equals 0. I need to understand these little bits. So using precision. Negative in 0 check. Immediately return false if it's less than or equals 0. Okay, fine. Makes sense. That makes sense to me, because you can't get anything less than 1 if you're going powers of 2. Because powers of 2 only goes down to 0, right? So then, okay, bit manipulation check. N to the power 2 has exactly 1 bit set in its binary representation. Checks has exactly 1 bit. If this works because the power of 2 binary has exactly 1 bit set to 1. E.g. 1, 10, 100. Subtracting 1 from a power of 2 flips all the bits after the first set bit, resulting in bit set being lowered to 0. This approach is efficient. Time complexity avoids the precision issues associated with flow. Okay, so this does make sense to me. Explain this further. Let's go through the bit manipulation technique. N and n minus 1. 2 to the power 0 is 1, 0, 0, 0, 1. 2 to the power 1 is 0, 0, 0, 2. So let's look at the representation. 0, 0, 0 thing. 2 to the power 8 is 1, 0, 0, 0. Notice that in each case, the binary representation of a power 2 has exactly 1 bit set to 1. That makes sense. Subtracting from a power of 1. Subtracting from power of 2. 1 from power of 2. Okay, so then I go n minus 1. N and n minus 1 equals 0. So let me close this, let me close this, let me close this. Okay, subtracting n minus 1, so n minus 1, so 8 minus 1, 0, 1, 1, 1 binary. 4 minus 1, 1, 1, 1 binary. In general, subtracting 1 from a power of 2 flips all the bits. This pattern occurs because when you subtract 1 from a binary number, you borrow from the left. Okay, flipping bits as you go. Okay, that makes sense to me. Bitwise AND operator, n minus 1, compares each bit of the two numbers and results in 1 if both bits are 1. Okay. Oh, okay. Okay. That makes so much sense. Because what you're doing here is you're taking n, which is going to be your 1 flip bit, and you're going n minus 1, and then you AND bit all your things. So, for example, let's go on the whiteboard here. This is what it's basically trying to tell you. And this actually avoids the size complexity with the, if you go if you go logarithms using math.log, with your floating point. So I'm going to show you guys here. So for example, let's say I have the number 4, or let's go number 8, because this one will be a clean example for you guys. Let's go number 8, right? 8 would be 1, 0, 0, 0. So this is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Okay, so 2 to the power of 3 is 8, 0, 0, 0, right? And then when you go n minus 1, you're basically saying borrow 1 from everything. So this becomes a 0, this becomes 1, 1, 1 to make a 7. So if we go here, this would be, so if n equals 8, n minus 1 equals 7, which is going to be represented by 0, 1, 1, 1. So if you see here, we go 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and then 4 plus 2 is 6 plus 1 equals 7, right? So that's good. So we have n ampersand n minus 1. So we want to check if that's equal to 0. So when we do that, we're basically lining up these bits, because it'll only equal 0 if there's one set bit. Because whenever you have a power of 2, you have one set bit. When we say a set bit, something that's set is anything non-zero, right? So in terms of binary representation, you'll only have 0 and 1. So 1 is automatically, by default, your set bit. So we go 1, 0, 0, 0, and then we go 0, 1, 1, 1. So when we do an AND comparison, we're just comparing each bit in the line. So you can only, if you look at your logical AND gate, right? If you have 1 and 1, the output is 1. If you have 1 and 0, the output is 0. If you have 0 and 1, your output is 0. If you have 0 and 0, your output is 0. So this is the only case where you'll have an output of 1. So if we compare this using an AND bit, it compares the bits. So if we go back to here, n and n minus 1 equals 0, we're saying, okay, we want to check if there's one set bit. That's all we're doing. Because by default, if you have an n minus 1, all the other bits are going to be 1s, like this. You have 8, so if you go n minus 1, you get 7. All the opposite bits are 1. So if you had 0 and 1, that's a 0. If we go by this chart. If you go 0 and 1, that's a 0. If you go 0 and 1, that's a 0. If you go 1 and 0, that's a 0. Therefore, you get 0, satisfies the condition. So if we go here, anything less than or equal to 0, right? Because 2 to the power of 0 is 1. So if it's anything 0 and less, return false automatically. Then we check to see if it's a set bit. So if it's if there's one set bit. So if it's a power of 2, you will have one set bit, because when you go power of 2 and n minus 1, you automatically cancel out like we did here, right? And if we do that, we can submit this. So we can run it, submit, and there you go. That's the answer to the problem. So if you like this video, please leave a thumbs up and subscribe to the channel. Leave your comments below. Peace.